Now we're going to expand our earlier lecture where we broke a data set into a training and test data set. And now we're going to actually build some models, or we're going to revisit some models that have already been built, and we're going to show how this could be used for validating that the model is pretty good. So we're going to go back to our friend the IRIS data set. So if we do the head command of IRIS, and if you recall, IRIS is a data set that's already present in R. You can see we have 5 records, and we have 5 fields here. So we have the sepal length of the iris, the sepal width, the petal length, and the petal width, and then we have the species. And if I do the dimension command, you can see we have 150 irises and we have 5 columns. 1, 2, 3, 4, 5. Okay, let's start by first loading, and we're going to build decision trees like we did in an earlier lecture. So let's load in the libraries for the decision tree. So that's our part and our part plot. That's going to allow us to draw the decision tree. Let's set our random number seed, and we will come over here. Now, when you run this, it might, well, let's first create the flag variables again. And I'm going to have 70% of my data be training and 30% be testing. Why did I decide that? There's no real standard rule that you have to follow. You can go with, I usually start off with 75-25 or 70-30 or 60-40, something like that. I start off like that and I kind of adjust it up and down. If my model isn't training very well, I might add more to the training set. So if I can't really find a good model, I might make it like 80-20, because if I give it more data, it tends to give me a better model. But if I think that I'm not quite confident with the model, I might move this number, the test set, up a little bit higher to validate, to be very certain that the model I'm building is actually pretty good. So let's come over here and let's create this flag variable like we did in the previous lecture. And then we're going to say iris, and then the flag variable here is going to be the 70%, and it'll go in here into the train data. And when this is set to not flag, it's going to go into the test data set. So let's do that real fast, and let's see the dimension. And you can see here that we start off with 150 records. 106 of these things will go into the training data set, and 44 will go into the test data set. Now, if I run it again, the random number generator is going to select different records for training and test. So let's just see that real fast. And now we have 111 and 39. So this is, we can just keep doing this. And in this case, I have, we're just going to keep building models. But you can see that every time I run this, it's like, rolling dice or shuffling a deck of cards. It's going to give us a different distribution. It's going to put different records in different buckets. So now what I will do is I'm going to train. I'm going to say, I'm going to decide that the decision tree should go no deeper than 2 levels because, well, this is a really simple data set, and that's what we're going to do. I mean, I just know this one. So let's go and do that, and then let's build a decision tree, and we're going to build the decision tree on the training data. And we're going to use all of the records. So we say the species, we're going to predict the species of the iris using, when we put a dot there, it's going to use all of the records. And then let's draw the decision tree. So let's do that real fast. And there we have it. You can see that the distribution of the Virginica, setosa, and versicolor irises, in this case, it's 29, 35, 36. In the real data set, it was 33, 33, 33. They were the same, but when we start shuffling the deck a little bit, it's not going to necessarily be an even distribution, but that's okay. Now you can see here, if the petal length of this flower is less than 2.5 centimeters, then it's going to be a setosa. Otherwise, we look at the petal width, and if it's less than 1.8, it's going to be a versicolor, otherwise it's going to be a virginica. Okay, so how good was this? Well, let's come over here and let's predict using the training data. And then, whoops, let's see what we get. So you can see here that we have predicted using the training data and the decision tree that we created, and it's going to say, okay, the first record is a setosa, the second record is a setosa, etc. And then you can see that the model has built, has said, okay, of this training data set, we have 32 setosas, we have 38 versicolors, and 36 virginicas. How accurate is that? Well, we can just come over here and calculate the accuracy. And you can see that the accuracy here is 95%. So it's 95% accurate in identifying flowers. But that is on the training data. We don't want to look at the training. Now we want to look at the test data. Because the test data is data that the model has never seen before. So if the model is any good, it ought to come up with an accuracy pretty close to 95. So how do we do this? Now recall that we got a test data set right here. So we're going to say, okay, let's use our decision tree and let's predict the test data set. This is data we've never seen before, and let's see how accurate that one is. Now, if our model is any good, we should be something close. And look at this, we got 97% accurate. Now that means that our model is probably pretty good because our test and our training data are kind of the same. And if the test data was extremely low, like we have 95% here, and we have 20% here, that usually means we have a bad model. Probably it means we have overfit. Okay, so if this number is bad and this number is bad, that means we underfit. If this number is good and this number is bad, means we overfit. So underfit is if everybody's bad. If training and test are bad, it's underfit. If training is good and test is bad, it's overfit. So this looks like it's pretty good. But you can't just go with that. Now what I will do is I'll try to run it again because maybe we just got lucky. So why don't we do this again? Let's take let's create a new flag and let's create a new training and a test and let's run these guys. And so now it's 101 and 49. Okay, different records. Now remember what this guy looks like, 2.5 and 1.8. So let's build a decision tree and plot it. Now this might not be exactly the same. It might be a little different. Trees are kind of like funny that way. They might be a little different. Might be the same. This is a real easy data set. We'll see. So this one stayed the same, 2.5, but this one dropped to 1.6. Doesn't matter. Still looks about the same. A small petal length is a setosa, and a small petal width is a versicolor. So that's a way of differentiating these things. Now, how good is this? Well, let's find out. Let's see what the training data says. Well, the training data says 97% accurate. That's great. Now, if our model is any good, the test data should be close to 97%. Uh-oh, 89. Okay, that's not real good. It's still pretty, it's still pretty good, and I would probably use this model with that 89%. It's still close, but it makes me go, okay, maybe this isn't the world's best model. Why don't we run it again? Maybe, what I want to do is I want to consistently run this thing, and when I start getting similar accuracy over and over again, then I have confidence that I got a good model. So let's just for fun do it one more time. So let's come over here. Let's come up here to the top. Let's recreate the flag variable again. And let's go down here, do a training. Let's just run the training and let's run the test, see what we get. And our training data had a 96% and our test had a 91. That's pretty good. They're similar. 2.6. Ooh, pedal length is less than 5. Well, I see. Interesting. This time he split on pedal length and not pedal width. That's an interesting thing. Trees are like that. They can be a little bit variable, but that's okay. But this is making me, reasonably comfortable that these numbers are close. They're not always going to be great, but they're close enough that I have confidence in this model. Let's go a few more times. Let's do it one more time. One last time. And now we have pedal length again, and we have what? 97% and 91%. Okay. So what this is telling me is that because we consistently are getting good training and good test, this is telling me that using a decision tree with 2 levels is probably a pretty good model. Now, because I know that, I'm going to say, okay, once I'm comfortable with the model, now I'm going to train on all the data so I get the best possible model. So let's do this one last time, only now I'm going to put all of the data into DF. Okay, and now I'm going to build the decision tree on DF on all of the data, and I'm going to plot the decision tree. Let's see what we get. See, 1/3, 1/3, 1/3, pedal length, pedal width. And now let's just see how accurate this is. 96% accurate. That number is pretty close to the numbers we've been getting up till now. So I'm pretty confident that this model will be the one that we will use. I test it on I build it on a training data set, I test it on a test data set, and I make sure that the numbers are close. Then I do it again and again and again. And when the numbers are consistently close, I'm done, and I build the model on all of the data. And that's the model I'm going to use. So this is what we've just done with the IRIS data set. Now we'll go and take a look at the insurance data set in the next lecture.